Okay, hello everyone. Let's talk about fast division. So, this one is actually one of my favorite topics in 105, just because fast division is um, it's quite complicated, but it's very rewarding when you understand how it works. So, first off, this is why you should pay attention. Intel once had a bug in the Pentium processor. So you can remember that was like a very, very long time ago. Even I don't remember it. I wasn't born yet. But or at least I don't think I was born yet. There's Pentium 1 to 5. I'm not sure which one this Pentium 1 this Pentium was, but it's probably Pentium 1, which is sometime before 2000. But basically, they had a bug in the processor about floating point division. So floating point is something we haven't talked about it, but yet. But the division part of the floating point division is something that we're going to talk about now. And floating point will be talked about next. So basically, listen to the next two lectures if you don't want to be fined $475 million, or you won't be fined yourself, but you're going to be costing your company $475 million if you get this wrong. So that means that binary division, not just floating point, is hard. So maybe we want to see how exactly it would be hard. So we can actually do binary manual long division. So I would use this example. We have 5 and 135. So in decimal, manual long division, you first try to divide the first number with the number that you have. So 1 divided by 5 does not fit, so you have 0. So that's 1 minus 0, that's 1, and then you bring down the 13. And then, okay, does 5 fit in 13? Yes, you can fit two of them. So you can have 5 times 2, and you have a remainder of 3. Now you just bring down 5, and you get 35 over here. So how many 5s can you fit in 35? That's 7. So that's 7 times 5, you have 35, which from which you get 0. So 0 to 7, we've spent all of the bits already. So we have everything aligned with each other. So we have remainder 0, which is just 27. Now, what do we do if we have to do binary? So let's say we want to divide binary 1000 with binary 1. Um, I'll just say now this is basically 8. Um, right, that's 1, 2, 4, 8 divided by 3, which is 2, remainder 2. So we want to find the answer 2 remainder 2 using manual long division of base 2. So first, we try to fit 1 in 1. Clearly, 1 is the lesser number. So we have 0. We can fit none of that. And 1 minus 0 will still be 1. We bring down this 0. Have 1, 0. How many 1s can we fit in 1, 0? That's a 2, that's a 3. We can't fit any. So that's also still a 0. Then multiply. Get a 0 over here. So 1, 0 minus 0 is still 1, 0. You bring down the next 0. You have a 1, 0, 0. Now, you can fit one of these. Actually, you can only ever fit one of this into that, because if you can fit two, then this would have been one. But anyway, you multiply those, and then that's a 1, 1, and 1, 0, 0 minus 1, 1 is actually 1. You can confirm by just doing the reverse operation. Just 1 plus this is actually equal to this. You can see that. Now we bring down the last 0, and we find that this thing no longer fits. So that's 0. But that's all of the bits that we have. We have encountered the end over here. So we just take this as the remainder. So that's 1, 0, remainder 1, 0. And voila, that's 2, remainder 2. Yay! So that's how you do binary long division. It's basically the same as decimal long division, but you just try to fit things. You just say 1 if it can fit, and then you subtract, because it will never not be. It will never fit more than one of the previous number. Just because of how binary works. So all you actually need to do is to compare which thing is larger. So you see we had these intermediate operands. So we tried to confirm, is 1 1 bigger than this one? No. If one is 1 1 bigger than this one? Well, is 1 1 bigger than this one? Yes. Is 1 1 bigger than this one? Yes. Is 1 1 bigger than this one? No. So subtract it, and then we get this. Is 1 1 bigger than this one? No. So you have and the series of answers to that actually. So this one we answered no, that's 0. This one we answered no, that's 0. This one we answered yes, that's 1. And this one we answered no, which is this one. So and that's an exciting thing, and that's basically the essence of the algorithm that we're going to be discussing next, which is how to do division in terms of binary logic or sequential division. We're going to define some terms here. M is the divisor, and Q is the dividend. So basically, we're calculating Q over M equals, well, uh, Q after remainder A after. So, okay, the A holds the remainder at the end, Q holds the quotient at the end, but it is initially the dividend. So, that's basically this thing. So, let's talk about restoring division. So, restoring division is based on manual long division. I will show you that. So, at the start, we pair n plus 1 bits of m and m complement, and then we prepare an empty n plus 1 bit a. And then you can just read this, but it will make sense later when I show you how the restoring division works for the long division that we made earlier. But here, I'll show you how this is related to the long division that we did. We divided 1, 1 with 8. So here, um, A is actually the intermediate operands that we had. So actually, at first, this is A. So A equals 1 in the first iteration. We compare. So is 1 1 bigger than 1? Okay, is A greater than 1 1? So 1 1 is actually M. So is A greater than M? No. So that's 0, which is the first bit that we put into the Q, because this is actually the Q. Now we multiply that, so we get 0, and then we subtract, and then we add the next bit, and then this is the new A. So A equals 1 0. Is this greater than M? No. So that's 0, and then we multiply again. So we bring it down, and then we bring down the next bit. Now A is equal to 1 0 0. Is that greater than M? Yes, it is. So that's 1. And then we multiply. It's 1 1. So if we subtract, we get 1. Then we bring down the 0. And now A is 1 0. Is this greater than M? That's a no. And that's 0. So we add 1 0 again. And now at the final state, this is A. And you have a Q up there. So that's Q remainder A, which is 1 0 or 1 0. So now you see, in terms of the, if we name these things, and these are the same names that we're going to use for restoring division, but you can see that this is actually a sequence of shifting. So you can see here, if you shift each bit of this thing into A every time, unless something fits. If something fits, you subtract M. So the subtract M becomes this thing. And then if it doesn't fit, well, you shift in more bits. But eventually you run out of bits. You can see we only have 4 bits here, so we only had to do the thing 4 times. So now let's do restoring division in terms of the restoring division algorithm. So it said we have to prepare an M and the complement of M. So M is 0 0 1 1. said n plus 1 bit, so we had 0, 0, 0, 1, 1, and the 2's complement of m is 1, 1, 1, 0, 1, or the 5-bit 2's complement of m, the n plus 1 bit 2's complement of m is 1, 1, 1, 0, 1. And we have to prepare two registers, A and Q. Register A has n plus 1 bits, so that's 4 plus 1. And Q has initially the dividend. Okay, so the restoring algorithm basically works as follows. So for iteration 1, you shift the thing once, and then you think about what this bit, we're going to derive what this bit will be later. So first, we see that we subtract m from a, so that's a minus m, so that's 1, 1, 1, 1, 0, and then we look at this, and then we put that, the complement of that, into the shift in bit of q, which is 0. And then we saw that since this is negative, we restore it back to positive, and then we continue. Continue by moving on to the next iteration. So shift again. That bit is unknown for now, and then we add negative m, and then this is 1, so that's 0, and then that's 1, so we restore. So iteration 3, that's 0, 0, 1, 0, 0, 0, 0, 0, blank. And now we have we subtract m again, so that's plus 1, 1, 1, 0. Note that the next bit over here will be discarded, so that's since this is 1 plus 1, 1, 1, that would be 1, 0, 0, 0, and that's discarded. 0, 1. So okay, this thing has been discarded. This is the signed bit, so we put in 1 here. And now for iteration number 4, what we have is note that we don't do a restoration here because the sign bit is 0. It's a positive number. We don't need to restore it back to positive. So for iteration number 4, we shift. And then we subtract, okay, we don't know this yet. We subtract m again. So that's plus 1, 1, 0, 1, which is 1, 1, 1, 1, 1, 0, 0. And then that's 0, 0, 1. This was blank, but it's the complement of this, which is 0. And then since a is now negative, we restore from here to here. So now this is the remainder, this is the quotient. So 0, 0, 1, 0, remainder 0, 0, 1, 0. That's basically how the restoring division works. And okay, so I hope that was clear. You can look at the slides again in order to like absorb it more deeply. I'm going to upload 2 sets of slides for this actually, so that you can see better how restoring division works. But next we have another type of division, which is the improved restoring division, as I like to call it, or the non-restoring division. So this time we're not going to restore a if it's negative. We're just going to keep a if a is negative. So what happens here is let's do the let's do the sorry let's do the previous example again. So we have 0, 0, 0, 1, 1 and 1, 1, 1, 0, 1 for m and m prime respectively. And let's do this this non-restoring division procedure. So initially A is 5 bits of 0 and Q is the dividend, which is 1000. Now that's A, that's Q. If sine of A, so we look at the sine of A, if sine of A is 0, let's put this one down here. Sine of A is 0, then we shift to the left. By the way, spoilers, we always shift to the left, so might as well just do that. But we look at this and say, okay, since it's 0, we subtract. So that's 11101. So we have 11110. And then this thing turns into that thing again. So that's 0. But we keep this. We keep whatever this is. So that's the start of iteration 2. Okay, so the start of iteration 2, this is 1, so you add. So after shifting, you add. So we're going to shift first. So we don't know what this is. And then we add 0011, which is 11111. And then the shift in bit is 0. Is going to complement again. So that's the start of the next iteration. So this is going to be an add again. First we shift, so that's 11110, 000, 00 blank. We don't know the shift in bit, and then we add again 0011. So positive M. That's 1, and then this is all going to be 0 with the carry bit 1, but we throw away the carry bit, so we just get 00001. And then now that the sign bit is 0, we make that 1, and we go on to the fourth iteration. So fourth iteration, we shift by 1, and then that's blank. And then from this being 0, we know that we should add M prime instead. So that's 11111. And since this sign is 1, we put in the opposite, which is 0. And at the end of non-restoring division, rather here, at the end, if A is negative, A plus M. So basically, non-restoring division is also still a restoring division, but you do restore only once. So what you do is you restore back to the A that's the last A that was positive at the end of the division. So A is basically A plus M. So this thing plus M is back to before you subtracted M, which is this one. So now here is R and here is Q. And those are basically the same answers as we had before. This is 2 remainder 2 as well. So that's the answer for the non-restoring division.